All right, so for the second part of this session, we have Enea speaking with us. Enea is a PhD student with Monzio at University of Basel. And he's going to talk to us about traffic-aware minimization and how you can model S with an SDE as you expect to be expert.
Exactly. Thanks. This is a joint work with Luca Biggio, who was not here, Antonio, who presented a couple of days ago, Frank, Aurelion, and Hans. This paper was accepted at ICML 2023, so I'm going to present it in Honolulu in a month or so. So, okay, let's see how it works. Good. So I'm going to give a little bit of an introduction. Then I'm going to present some versions that we studied. I'm going to go over some related works, our findings, and then draw some conclusions. Now, this is an informal result, which we didn't derive. This comes from Foret, who first proposed some sharpness-aware minimization. What they claim is the expected loss over the distribution of your data. So the whole distribution, you can dominate it with this quantity here. Okay, so this is the expected loss on your data set. And this here is a perturbation which has a small norm rho. Okay, rho is like, you can imagine it as a radius. I probably will draw something. And then this increasing function here. Now the idea is, okay, how can we reduce this quantity here? Okay, so in general, we want to minimize the training loss, right? Or you have like some data, you want to minimize the training loss. But if you want to like, if you want to push down this error here, okay, you have to first solve this maximization problem here over this little ball of a radius rho. Okay, so you have to find let's say optimal perturbation, a worst case perturbation. And if you just rewrite the expression up here, this bound in this way, you see that this doesn't depend on epsilon, this neither, but this quantity here has a clear interpretation. It is the maximum increase, okay? If you are here, this is your x, and you perturbate of epsilon. This is the maximum increase you can ever get. Okay, so if you are able to push it down, it means that you arrived in a flat area. If you perturbate of epsilon and this is a small increase, it means that you are essentially in a flat area. Okay, this is kind of intuitive. Now, yes.
S is the random thing, right?
S is your data. F, it's hidden, but this is an expectation of the loss over the training set. And this is the expectation of the loss over the whole distribution of data.
So S is the empirical average, right?
Empirical, yes.
So it's the random quantity you didn't think about.
No, it's hidden. It's already an expectation. It's already an expectation. I can show it on the paper if you want. I can.
It's an expectation of a random measure, presumably.
Well, yes, of course. Yes, of course. It's just
it looks like a deterministic equation, so
it is. It is.
So there should be a couple of expectations which I cannot.
They are hidden. They are hidden for in a way. Yeah, you're right. It could be confusing. I will improve the presentation. This is the first time I present this. I just took the paper as it is on the original paper, and I tried to explain what it means. But I see that maybe it's better if I put a little bit more. Now, so again, if we look at this, okay, this is, as I said, the maximum increase from x to a certain other set of parameters inside, with a perturbation inside this small ball, okay? And if you just try to solve this problem here, you can just do a Taylor expansion, throw away some terms, and then say, okay, the optimal perturbation is actually rho, multiplied by the gradient and divided by its norm, okay, so that it is of size rho. In a way, it makes sense, right? You are in a certain part of the landscape, right? You are here, and you say, I want to find the worst possible direction I can go to. Well, usually you want to minimize the loss, so usually you go down on this quantity, right? Well, the way to make it worse is intuitively to go upward in the very same direction, but opposite. Person. So instead of going downhill, you go uphill. Okay, this is a way, the way they do it. This is exactly what so a representation, a cartoon representation is. You're here. Usually with gradient descent, you would calculate the gradient and go down. Instead, what they do is they take an upward step of a size rho. They calculate the gradient, and then instead of moving from here, they take this new gradient here and they apply it here. Okay, so instead of going down with gradient descent, you go up, calculate the gradient, and then you translate it here, and then you move. Okay, this is essentially a cartoon representation of what is happening. Now, why would you ever do this? Well, as I said, what you want to, if you do this kind of choice of perturbation, what you're trying to aim is to reduce this jump here. So if you're able to reach that this jump is small, essentially you're in a flat area. And again, you should ask yourself, why would I ever want to be in a flat area? Well, because this makes you robust with respect to shift of distribution of your training data with respect to the test data or through of the whole possible distribution D. So it's essentially it's better to be in a flat area because, like also intuitively, if you are in a sharp minimum here and you change a little bit your parameters, the loss increases. Maybe your functional and the function that you're learning also changes a lot. Well, if you are in a flat region and you change a bit your parameters, essentially you stay the same. Okay, I hope it makes, at least from a mission perspective, sense. So here is the iterations of the algorithms, the iterations of the algorithms that we treated. This is SAM. Okay, so you start from an iteration K, then you take the upward step, you move in that upward direction, you take the gradient from there, gamma K is the mini batch, okay, that you draw at every iteration, and then you use this gradient, you translate it back to your iterate, and you use it. This is exactly different, the algorithmic version of this cartoon here. You see, gamma K, you go up, calculate the gradient, translate it back. This is exactly what's happening. Now, Andryshenko and Flammarion propose a different algorithm where you don't have this normalization here. They did it essentially because it's easier to treat theoretically, which is fully true. However, we noticed, and it has been noticed, that these two algorithms don't really behave the same. So we introduced, let's say, a proxy one, which is in a way kind of in between, because it's not exactly the same. As you can see here, the gradient is full. So this algorithm is absolutely not meant to be used in practice because you cannot even calculate this quantity in many cases. So this is just a theoretical tool that we use to gain insight into SAM, because USAM actually behaves quite differently from SAM. So it would not give you the correct insight.
K is a mini batch or size 1 or?
Oh, no, any batch. Any batch. It's a gamma K is a mini batch of size B, whatever it is. Yeah. So what is known about the SAM dynamics so far? It's relatively a new optimizer. It was done in 2017, so it hasn't been around too much. And why do I study it? Because it works. Essentially because it actually works. It actually finds flat minima. It actually generalizes better. It's used like in real settings, not only a theoretical effort. It's an optimizer that works. Now, so SAM, people prove that it actually implicitly minimizes a regularized loss that drives the dynamics toward the flatter regions. Okay? Yes.
How do you define flat?
Yes, you're right. This is a good point. Again, something that I should add in my slides. It is the Hessian, the trace of the Hessian, okay? Trace of the Hessian in X is the measure. In a way, you can imagine if the trace is small in a minimum, it means that all of the eigenvalues are small and therefore you're in flat. Makes sense. Maybe it's not unique, it's not the best, maybe way to measure flatness, but this is very common.
So if you are at the 7 point, this might be 0.
it could be zero, despite not being flat. Absolutely. That's why actually some results actually prove that it is the largest positive reading value, which is small, that it is trying to minimize. So yes, absolutely true. It said, oh, it's a tricky measure because you need to compensate. Now, other results are convergence result of different classes of functions, depending on the regularity. It tells you like, okay, it's going to converge with more or less speed, depending, it also depends on raw. So there are some results on convergence, which are very popular in the optimization community. And then some people derived an ODE approximation, so an ODE model, ordinary differential equation model, to study the behavior of this optimizer if you send the learning rate down to 0, okay? Now, what we did instead, the title suggests, is modeling and the stochastic SEM. So when you draw mini batches with an SDE, so a stochastic model, it's essentially what you're trying to do is to formalize a continuous time model that behaves like the discrete one, okay, in a certain weak sense, meaning that the moments of the increments of the discrete time algorithms are very, very close to the one of the continuous time one. Okay, this is what we're doing. If you want the formal definition, is in the last slide, but as you can see, I'm trying to keep it as less formal as possible. I'm trying to give more intuitions. So why would we ever do this? I mean, as these have been used before, we have seen it many times these days for SGD. It was derived, it was made it completely formal in 2017. That is a good model. You can prove that that's a good model from a theoretical perspective under some assumptions. And then they have been used for doing like optimal control on the learning rate, scaling rules, exit times. You can do all sorts of stochastic calculus based on these SDEs. So you can use techniques that you could not use on the discrete time algorithms. Okay, and then you can hope that your insights carry over to the actual algorithm, because you can always, you always have to think the discrete time one is reality. And then there is your continuous time model, which might introduce artifacts. It might be only valid under certain assumptions. So you always have to be still careful when you use it. But you can use stochastic calculus, which is the fun part. Now, how can we use SDEs to explain how some escapes from sharp regions faster than SGD would do? How does the curvature of the landscape, which is again related to the Hessian, play a role into these whole dynamics? And is it possible that actually this optimizer gets trapped somewhere, so they get stuck, and then they are not as good maybe as SGD at escaping them, aka saddles? We know that SGD runs away from saddles. We will see that SAM is actually slow at that. It's way slower. Not only theoretically, also practically. So we have seen experiments. Now, let's remember that this is the SDE of SDD, okay? It's a so-called order 1 week approximation. Again, the idea is the average, the variance, the third moment, fourth moment, fifth moment. They are kind of, they are very similar of the increments, of this object here are very, very close to that of the true algorithm, okay, meaning that the error is linear in eta, okay, the error is linear in eta. If it was a second week order, it would be quadratic in eta, so you would get a better approximation. But this is the first order one, and what we derive is an SDE for SAM, USAM, and BN SAM, and what we find is that if rho is sufficiently small, so the same order of magnitude as eta, then actually they also behave with this SDE. This SDE is also the SDE of this algorithm. So essentially, they kind of behave the same. You cannot claim that there is something more, okay? But if you allow rho, so the upward step, to be a little bit larger than eta, which is actually what happens many, many times in current applications, then you can prove that the dynamics of SAM, USAM, and the other guys is equivalent to that of SGD on an implicitly regularized loss, which is already well known. So this is not something that we prove. This is just like finding something that is already in the literature. what we find is actually that these methods have an additional implicit curvature-driven noise, as I will show in the next slide. Yes.
Sorry, what do you mean what a one big approximation to the stochastic gradient descent?
What?
What does this mean? It's in quarter one.
Yeah, you're right. I go to the last slide for a second, and I show you this. It's a little bit unreadable, but only read this. Maybe just read this. G is a test function, any function, a polynomial, a regular function, whatever you want. Let's stick to polynomials, okay? So the expected value of the increment of the discrete time algorithm is very, very close to the expected value of the increment of the continuous time algorithm, meaning that this error decreases linearly in eta. Okay, then let's think now G is the square, so it's essentially, let's say, the variance. Okay, then also the variance of the increments is similar. Then you can put it for every test function, and then you realize that essentially they are similar in distribution. The increments are very similar. Yes.
So I find it a little misleading what you are saying actually, because this constant C increases exponentially with n, and the constant C over there. So if you run the algorithm, this approximation is going to be exponentially better. So
That's true.
I mean, I wouldn't agree that this is a very good model for SGD in any case, just because the moments are matching for a short amount ahead.
That's true. That's true. Somehow, though, if you think that it is true on a small time scale, you can always patch together different SDEs, right? And then you can patch together the SDEs at different initialization, and it's always good. We have indeed some experiments where it is like good for I don't know, 5,000-10,000 training epochs, which to me seems very, very good.
Well, yes, but like this theorem, I think doesn't apply that. But empirically, I agree. So
Okay,
then
then
it's a theorem from the DF. But I like the definition, but they use like the way this is derived using theorems from numerical analysis for stochastic.
Yeah.
It's like, and then you show that this the discretization, the way Euler-Maruyama.
Right. You just think about the terminology, because for me, as a stochastic process guy, I would say the other way around. For me, stochastic gradient descent is the order of approximation.
yeah, right. This is usually what happens, but they are doing the opposite because you're right. You're right. It's true. Usually you have the continuous time, and then you discretize, and then you find the discretization. But here we start from a discretization, from discrete time something, and we want to revert. You're fully right. It's a great observation.
But I was just thinking. I mean, maybe you're right, but like, no, are you sure that it depends C in the end?
I have no idea, but if you say so, no, I take it.
They had some.
Yeah.
It's good by argument. Okay, all right. All right.
I guess the question would be, are there better ways to do this? Because when we observe in the literature, this was pretty much the only sort of theorem you find. So are there other alternatives to this?
I would be happy to know.
So I'm really not an expert on this, but one point I have interest in this question, and sort of is accelerated, schemes for the try to do stochastic gradient and other ways and so on. And there's some papers by Emmanuel Coudes and Portos.
But it seems there's on this, where they essentially absorb all the deep from. Yeah, exactly. But if you don't have any guarantee that it's probably the right, I don't think they. I think so. In this one, I think they right it so more. Yeah, exactly.
No.
This is something called shadowing. That's why I don't really work on this. There's some concept in dynamic system where they talk about this about shadowing. We have some sort of proximity measure, but I thought that was more.
So it might be
Repair is not the ideal thing. I think the moment you look at repair, I think there's no way to escape.
Is there something other than this?
I feel there should be, and then I think the main reason why I look like this weak error is that we need to use a very small step size to like make any argument. This is not what's happening in practice.
I agree.
I partially agree with this actually. I only partially agree because you can test it numerically, and then you see that also sizable learning rates actually do a very good job.
I can also test that.
Yeah. There is always, I'm not saying this is. No, I'm not saying I'm God and this is the best model ever. ever. I will not explain this. It works to explain some models under some assumption, but everybody's welcome to do to build on this. I'm more than happy. But this is a model.
It's likely also be something people are taking up machine learning now. So they're not the only ones to use it. So it's like maybe if there's something better, that could be a good time to put it out there.
But like, I mean, as we just noted, like it's the other way around from where the like. So would we expect that there's a better way, like that? I mean, like it seems constrained by what the numerical analysts have thought about, right? Because it's the other way around to continue to tweak to continue. So it would be quite surprising if we can find something better, because then this would mean that in numerical analysis, it could also be a better algorithm that they have found, which would be kind of really surprising. So, no, but I mean, looking at the numerical analysis literature, like can go beyond it, maybe Enea was for one, but yeah, but if you're
Now, let's have a look at the SDE that we derived. Let's look at USAM. USAM is the one without the normalization step, okay? So you just go upward of rho gradient, not rho gradient divided by the norm, okay? So you go up of rho gradient. If you look at this, this is an additional term that, let's say, appears in the loss, and it is discouraging the algorithm. So it is encouraging the algorithm to go to minimize f, the loss function, but also to aim at point with a low norm gradient of the norm. No, norm of the gradient. Okay, so essentially a flat area, essentially, but without paying really much attention to is it a minima, is it a saddle, is it a maxima, because this doesn't encode any notion of convexity. Okay. What is interesting is you also notice that the term in red is on top of the SGD of the SDE of SGD. Okay, so there is this additional term here which is proportional to rho and also proportional to the Hessian, which again kind of encodes the curvature. Okay, because like the Hessian in a way gives you the idea of how the approximating quadratic is behaving locally. Okay. So you can imagine, let's say that we are in a minima. We are in a minima, and that so this is a semi-definite positive. So you can imagine that this is bigger than the identity, okay? Because I'm adding something on top of the identity. So essentially, there is implicitly more noise in a minima if I use a sum, rather than if I were to use SGD in the same minima. So this algorithm has implicitly more noise. It has more ability to escape a sharp minima than what SGD do. And we already know that SGD is pretty good at it. This is just faster. Okay. Now, DNSUM is like the fake algorithm that we introduced as a theoretical tool. And what we see is that it has a very similar implicit regularization. Okay, just the square is gone. So it has a stronger regularization as you get close to a minima. But on the other hand, look at the volatility term here. It is if you are in a minima or in a saddle or in a maxima, this is 0. So the implicit noise actually explodes to infinity. Okay, so this tells you that in a sharp area, okay, this has way more noise than SGD, way more. It could also possibly explode. It is well known that sum does not converge to minima. So this could be an explanation, because the moment you get close to a minima, you actually get pushed away by extreme volatility. I have some simulation for it later. Now, actual SEM, this is the true algorithm, not USAM, not the simplified one, not the, let's say, proxy one that we, let's say, created. This is the true one. It's a little bit less easy to read. So this is still the Hessian as I define here. So still there is this component, rho, the Hessian, and then there is these terms here. You can imagine that in USAM, this term here is not there, okay? So you can imagine again, if we now think, like if we now look at what happens closer to a minimum, for example, this whole matrix here would be 0 for USAM, or very, very small, but for SUM, since there is this renormalization, this quantity here is a little bit more sizable. And also empirically, we observe that SUM indeed has more noise than USAM. So let's say all the interpretations and the insights that we get from this noise structure and the interaction with the Hessian makes sense, not only because the formula says so, but also when you simulate it, you observe it. So that's quite cool, I would say. Now, let's come to some pictures. Okay, so let's start from the quadratic model. So this is the quadratic model. So it's a quadratic, the easiest model you could ever imagine. So how does the error of SGD behave if I try to, so what's the error I make if I approximate SGD, the discrete one, with its SDE? It's actually zero, like flat zero. This is not zero because I'm zooming out. This is numerically zero because it's in a way, it's exact. It's for a quadratic, it's exact. Now, if instead I were to try to model USAM with the SD of SGD, then you would see that the error would increase. If I increase rho, so the larger rho, the more mistake I would be making because USAM is substantially different than SGD. And the same happens for SAM. If I try to model SAM with its own SGD, boom, the error is essentially zero. While if I try to model SAM to approximate SAM with the SD of SGD, which doesn't have the upward step again, then the error increases if I increase rho. While if you see also when rho is small, they all behave kind of the same. So the SD of SGD would actually be a good model because rho is so small that nothing is happening. Okay, so this graph is in a way makes me happy because it was the first experiment and it made sense. Everything worked fine. So we said, let's make a teacher-student model. So a teacher-student model works like this. Yes.
How do you choose the step size?
Yeah, you're right. The step size here is like 10 to the power of -2.
Quite large.
Yes, it's larger than, but this is 10 to the power of -3. This is like -2. This is also -2. But you can also make it bigger. It's really like not a ginormous mistake. Then, okay, maybe the graphs are not so nice. Sometimes you have like a spike in error, but it really works well. I was surprised myself. And so I think, sorry, teacher-student model. You can imagine I have so a teacher generates data. It's usually a complex model. And then you have a student which is trying to learn the pattern. Yes. I only have 5 minutes. Okay. So, okay. So this is not so interesting, the teacher of the student model. It's a little bit more complex and it still exhibits the same behavior. Then we had a deep linear neural network. So it's as easy as I say, you have input, linear layer, linear layer, linear layer, linear layer. So it's essentially not a real neural network in a way, okay? But it's more complex than a linear layer itself. But then if you also make it non-linear I think it's, these are like very easy data sets because, it makes it easier because I have to calculate the Hessian. You know, the Hessian is quite expensive to calculate and I have to do it at every iteration. Maybe I have to do it for 5,000 epochs, so I cannot have large data sets on large structures. So yeah, so this tells you the SDE actually approximates the algorithm quite well. So it's a reliable model. This is encouraging. Then this is just on the same models. This is the evolution of the loss function through training. You see, like this is 5,000 epochs, 1,000, 100, 10,000, 5,000. So it's quite a long time, and you see they almost match perfectly. So they are really mimicking one is mimicking the other quite closely. And again, it's not perfect. And here you see there is a little bit of deviation, but the error is, of course, it's there. It's bound on the error, not guaranteed. Now, what did we do with this? Because so far it was only what did you find? Okay, implicit noise, implicit regularization. But what did you do with it? Okay, what I see is that the deterministic versions of these algorithms, so no mini batch, the gradients are perfect. Okay, so they're precise. SAM and USAM actually have attractors, positive measure attractors around saddles. That's fun. It means that if you are close to a saddle, you're gonna stay there for a long time, possibly forever. And the SDE, you would say, yes, okay, SDE, like you inject noise, so these algorithms will be able to escape. Look, if you with the SDE, you can show that USAM actually stays there. on distribution, of course. So if we have on average, be centered around your saddle, move around a bit, but won't be able to stay. It's also quite fun. And also empirical validated. Here is like, these are 100,000 points that were initialized in different regions of the landscape, meaning around this saddle. And they actually distribute themselves around the saddle, but not in the saddle. Why? Because there is the implicit noise that pushes you away from the saddle. So again, the SDE predicted and the simulation confirmed. Interestingly, if you start a little bit off from the saddle, this is the number of points that are in a ball around the saddle. So there is like a, sorry, I have to go. This is the saddle. This is a ball that I decided the radius just randomly. We will do a bit of tuning to show this phenomenon. And then initialize points all over here. A lot of them, 100,000. Interestingly, what they do is they go close to the saddle, and then they are pushed away by the noise. So they go in and out, in and out, in and out, in and out, in and out. Not forever, because the algorithm diverges in the end from the saddle. But it takes like, I don't know, I'm going to show you now. It takes forever. SGP is just like, go, and he's happy. But some stays around quite a bit. This is an example not on a quadratic, because for the quadratic I could not prove it formally. But then I said, okay, let's see experimentally. This is embedded saddle. So embedded saddle, yes.
So in other words, one could maybe say to connect with Maxime's thought that if we would write a persistent exponent for the survival of staying in the saddle, that this exponent would be high.
Likely. If you can, just likely.
Probably very hard to prove, but experimentally that's like
What you're doing is essentially.
one does a log plot, maybe one can even look at the slope and that's it.
So an embedded saddle is essentially a saddle, quadratic one, where you add also a quartic term, so that you have a saddle in the origin and you have two minima next to the origin. So the idea usually is that you want to escape the saddle and go into the minima. Okay. Well, this is what happens. Gradient descent is this one is actually overlapped with USAM. They make the effort and they go away. Okay, but the original model, the true one that is actually used in reality, takes way longer to escape. In this autoencoder model, it's an autoencoder. If initialization autoencoder have a saddle, if you initialize them, well, USAM just stays there. This should continue, but it just won't escape. It lingers on. While the stochastic versions are a little bit better, nothing actually beats, I think, stochastic gradient descent in this environment. So for like these algorithms which are meant to look for good flat minima, then as a drawback, they have a problem in saddle. I thought also quite interesting. So to sum it up, it was already known that there is implicit regularization. It was known only for SAM. We proved it also for USAM. It is a little bit different, but it was not such a novelty. What we find is that there is an implicit additional noise, okay? And this is influenced by the local curvature. So the sharper it is, the more additional noise you have, the likelier you are to jump away from a sharp area and rather prefer a flat one. Then, so the implicit regularization actually drives this algorithm towards any critical point, because what they are discouraging, so what they are minimizing is the norm of the gradient, but the norm of the gradient doesn't encode curvature. And so they might actually have attractors which are bad, so saddles, because you don't want saddles. And they might just might not just stay in the saddle or around the saddle, but around the saddle for a long time. Then they escape, but still it takes time. And I think there is much more to do on this topic. Now, yeah, if you have questions. No, but I can show you here just for example, SDE here is gone like converged after 100,000 iterations, and SAM took twice, for example, here. While in this case, SDE converged after 10,000, and SAM is still around after 4 times as much.
In the scaling the dimension, the thing is small there. Something like D to find this SGP.
in the study. So whether the scale is higher than the.
Is it like a known result?
So I think, I see it as like phase retrieval. So phase retrieval, you have the salary representation. And it's known that it's a, couple of years old. Then this is become later once it's problem. But the same is not. Time or the paper for different things. Then you check that side like one of these, then you. Remember the papers? I can find, I don't know which book is the first one, but I think that is the page.
There is a lot of reserves, some basic points by Rondi and PG and a lot of people like some time.
But
Like,
I mean, like, I find the scaling and dimension hard to understand. I mean, because it changed the landscape in some sense, right? I mean, like, if you have a radius and you scale it and kind of make kind of contract the ball to the point, right? Like, or like, I'm just trying to understand what it means to scale a dimension, because it kind of you introduce additional dimensions. What it like? Basically, you escape from a different region.
there are multiple dimensions. The business rule essentially what happens for the action has zero eigenvalues in all dimensional directions except for one, which points towards the sea. Which is a minus because there is a dimension. But then